This lecture will discuss about prism, dispersion in prism, its chromatic resolving power, and different types of prisms, as well as microscope and its numerical aperture, and it will end with cardinal points in thick lenses. On dispersion in prism, it comes about because the refractive index of the prism material depends on wavelength. And from the total deviated angle that we calculated in the previous lecture, you can see that this expression here depends on the refractive index. As refractive index is wavelength dependent, therefore this total deviation is also wavelength dependent. In other words, different wavelength components of the incident light will be separated after undergoing refraction through the prism. Shorter wavelengths have larger refractive indices, therefore they will have smaller speeds in the prism. And the normal dispersion curve, which is given empirically by Augustin Louis Cauchy, and here it excludes absorption, is expressed in a simple form given by this equation. The refractive index is equal to A plus B divided by lambda squared plus C over lambda to the power 4. Where A, B, C are empirical constants which are fitted to the dispersion data for a particular material. And here is Cauchy, who is a famous French mathematician, engineer, and physicist. And dispersion is defined as dn d lambda. So when you differentiate this with respect to lambda, you will get negative 2b divided by lambda to the power 3 negative 4c divided by lambda to the power 5 and so on. Here this dispersion is approximated to only the first term, as the higher power of lambda will contribute less significantly. These two diagrams here gives an idea of how to differentiate between dispersion and deviation. Here we have deviated angle delta and the dispersion given by uppercase D here. You can see that the deviated angle from the original incident ray is larger, whereas for this one it is smaller. Whereas the dispersion here, which means the spread of the extreme wavelengths in the visible range, for example, is small, whereas over here it is larger. Dispersion can be characterized by using three wavelengths of light which is near the middle and the extremes of the visible spectrum, and they are called the Fraunhofer lines, which are absorption lines observed in the solar spectrum. These three wavelengths are given by 486.1 nanometer, which is characterized as F dark line and is the blue colored. And then we have the mid wavelength, which is 589.2 nanometer, and that's the dark line due to absorption by sodium atoms in the sun's outer atmosphere. That's given a symbol D. And the longer wavelength is given by 656.3, which is a red line due to absorption by hydrogen atoms, and that's given by a symbol C. Now, using a thin prism at minimum deviation for the D line, the ratio of angular spread of the F and C wavelengths to the deviation of the D wavelength given by this ratio here. So we have NF minus NC divided by ND minus 1 is called the dispersive power. The reciprocal of dispersive power is called the Abbe number. For example, in crown glass, it is 65. In flint glass, it is 29. And this is a photo of Ernst Karl Abbe, a German physicist. In the prism spectrometer, the prism is used as the dispersive device. And this is a simple diagram of the prism spectrometer. The prism is placed at the center, and rays from the light source passes through the slit and is collimated. And then this ray is refracted through the prism and collected by the telescope and brought to view by your eye. Chromatic resolving power of a prism is its ability to resolve two wavelengths which are very close. Let's consider a parallel monochromatic beam that's incident on a prism such that the beam will fill the prism face. Using Fermat's principle, ray FTW would be isochronous with ray GX here because they begin and end on the same wavefronts, which are GF and XW. Their optical paths then are equal, that is, FT plus TW would be equals to N times B, where N is the refractive index of this prism associated with a wavelength lambda. Let's consider a second wavelength, which is lambda prime, close to the first wavelength lambda, and the difference is given by delta lambda. And lambda prime here would then be associated with a different refractive index given by N prime, and that's equals to N minus delta N. Taking the incident beam to be in this direction with its wavefront Fg, both for lambda and lambda prime, and after passing through the prism, this lower beam here belongs to lambda, whereas the upper beam that is refracted from the prism is associated with lambda prime. And the plane wavefront for lambda is XW, whereas the plane wavefront for lambda prime is given by XW prime. And this lambda prime's beam makes an angle of delta alpha with lambda beam. And the angle between the two wavefronts associated with lambda prime and lambda will also be equals to delta alpha, such that this difference in distance here can be approximated to delta S. So the wavefront of the two emerging beams would be separated by a small angle here, which is delta alpha. Applying Fermat's principle to the second wavelength, we would get Ft plus Tw prime equals to N prime, which is equals to N minus delta N, multiplied by B, this distance here. And Tw prime is equal to Tw minus delta S. Delta S is given by the width of the beam, which is D, multiplied by delta alpha. Then we subtract equation 2 from equation 1. We will get delta S will be equals to B delta N. And substituting delta N with the dispersion term, which is equals to dN d lambda multiplied by delta lambda, then delta S will be written as B dN d lambda delta lambda. Now from the previous diagram here, delta S is equal to the width of the beam that is given by D multiplied by this angle delta alpha. Hence, delta alpha equals to delta S divided by D, which is the width of the beam. And substituting delta S here, we will get B divided by D multiplied by the dispersion term dN d lambda multiplied by delta lambda. And that's equation 3 here. When we consider the limit of resolution due to diffraction-limited line images, which we will discuss under the topic of Fraunhofer diffraction later, the minimum separation of the two wavefronts given by this delta alpha, such that the images formed are just barely resolvable, will be given by a ratio of lambda divided by d. Hence, equating equation 3 and equation 4, we will get lambda over d equals to b over d dn d lambda delta lambda, as given in equation 5 now. The minimum wavelength separation given by delta lambda mean, permitted so that the images can be resolved, would then be equals to lambda divided by b, and bring this dispersion term to the denominator on the left-hand side. Then we have this term here, and that's equation 6. Hence, the resolving power of the prism, which is an alternate way of describing the resolution limit of the instrument, can be defined as lambda divided by the minimum wavelength separation, and that's equal to b multiplied by the dispersion term. This expression tells us that we can improve the resolving power of a prism by using a larger B, which means a prism with a larger base. And the dispersion term here is limited by the prism material. Here is a quantitative example. We are to find the resolving power and the minimum resolvable wavelength difference for a prism made from flint glass with a base of 5 cm. Choosing the mean wavelength of 550 in the visible range, the approximate value of dispersion would be given by delta n divided by delta lambda, and that would be nf minus nd divided by lambda f minus lambda d, where these are the Fraunhofer lines. And this is obtained at a wavelength of 486 nanometer, and whereas this term here is at wavelength of 589 nanometer. Hence, this dispersion term here is expressed as negative 1.19 times 10 to the minus 4 per nanometer. The resolving power then will be given by the base of the prism multiplied by the dispersion term. And we convert 5 cm to nanometer units. Multiplying by this, we will get a number of 5971. Then the minimum resolvable wavelength difference in the region of 550 nanometer would then be lambda divided by the resolving power. That will be 5,500 angstrom divided by 5,971, and that's approximately 1 angstrom. This means that this flint glass prism with a base of 5 cm would be able to resolve a wavelength difference as small as 1 angstrom. In reflecting prisms, the beam is introduced in such a way that at least one internal reflection occurs. The purpose is either to change the direction of the propagation or change the orientation of the image, or both. The advantage of using reflecting prisms over mirrors are the prism's reflecting phases are easier to keep free of contamination because it's an internal reflection, and total internal reflection is capable of higher reflectivity. Here is a right angle prism whereby the incident ray is entering at this phase here, and it gets reflected at that inclined phase and exit in a different direction. the orientation of the image relative to the object is given here. Here is what we call a dove prism. It looks like a trapezoid. The ray enters from here and it gets refracted and it gets internally reflected at the base and it exits over the other face. Now, because of this reflection here, the orientation of the image is inverted compared to the incoming beam. This is a pentaprism with a pentagonal cross-section whereby one of the angle here is 90 degrees and the others are each at 112.5 degree. The beam enters in this direction, gets internally reflected here, and a second internal reflection occurs here, and then it exits over here. Many optical instruments use prisms to reflect light. For example, cameras and binoculars. When light is reflected internally by a 45-degree prism, as shown here, inversion occurs. In this case, the ray enters at the bottom face of the prism, gets reflected here, and reflected another time, and then it reverses in direction such that it will be anti-parallel to the incident ray. As you can see here, there's an inversion in the image. Now, this is an example of a prism. Here, it uses double prism arranged in such a way whereby the image is inverted compared to the object, and on top of that now there's a left-right inversion as well. Comparing it to the single prism, there was no left-right inversion. Prismatic binoculars use prisms in order to produce an image which is the same way round and same way up as the object. Let's look at a pair of prism that's arranged in this way. This is the object, and after reflecting internally here once, twice in the first prism, and then third time and the fourth time in the second prism, the image orientation will be the same as that of the object, which is shown here, whereby there's no left-right inversion and there's no up-down inversion as well. This is suitable to be used in the binoculars. Here we have the ray that enters, gets reflected in the first prism and then the second prism, and this goes to your eye. This system also has the advantage of a longer optical path because of the folding of the ray here, and that would allow for greater magnification. We are going to discuss about microscope that will act as magnifier, and we start with a simple magnifier, which is a positive lens. Consider an object of height h placed at position A here, and this is at a distance of 25 cm from the eye. This distance happens to be the near point of the normal eye, which is the nearest distance that we can still see a distinct, clear and sharp image unaided. And the angle that is subtended by this object at the eye, we will denote it as alpha 0. We would like then to project a magnified image on the retina of the eye, and we do this by inserting a magnifier, which happens to be a positive lens of focal length Fe, and we also move the object closer until it is at or just inside the focal point of the lens. This object distance S is less than or equal to Fe. In this case, we will be able to form an image which is virtual, enlarged, and it is upright. And the angle that is subtended by this virtual image at the eye would be alpha m. If the object is placed at the focal length of the positive lens, the image would be formed at infinity and parallel rays would be entering the eye. The lateral magnification will be very, very large, and that's not really very useful. Hence, it is more appropriate to define the image size formed on the retina by its angular magnification. And angular magnification is usually used when eyepieces are involved, especially in microscopes and telescopes. The angular magnification of this simple magnifier can be given by the angle alpha m divided by alpha 0. Here we have assumed parallaxial approximation. Alpha m can be taken to be equal to h divided by s and alpha 0 as h divided by 25. Then the angular magnification would be given by 25 cm divided by s, where the distance s is also in cm. If the image is formed at infinity, then s will be equal to fe, and the angular magnification will be given by 25 divided by fe. If the image is at the near point of the eye, that is S prime is equals to negative 25 cm, then from thin lens equation, we will get S equal to 25 Fe divided by 25 plus Fe. And in this case, the magnification will be given by 25 divided by Fe plus 1. Equation 8 here is often used for short Fe, as equation 9 here would approximate this value. Next, we take a look at image formation in a compound microscope. And the simplest form would be that formed by two positive lenses here, whereby this is called the objective lens and this is called the eyepiece. If we have a specimen here, the light from this specimen will be collected by the objective lens and it forms a real image. And this real image will become the object for the eyepiece or the ocular lens. The distance of this real image to the lens will be at the focal length of the lens or inside the focal length, and hence we will then see a virtual magnified image. In this case, it will be oriented the same direction as that image here. To minimize eye strain, then this image should be formed at infinity, which means that this distance here should be close to the focal length of the ocular lens. Instead of looking through the eyepiece with our eye, we attach a camera to the microscope, then we would need a real image to be formed. In this case, we would adjust this ocular lens, the eyepiece position, such that the distance of the image of the objective lens is now outside the first focal length of this eyepiece. And the magnification is given by negative L over f0, whereby f0 is the focal length of this objective, multiplied by 25 divided by the focal length of the eyepiece. In this case, f0 is very short, and the distance from the second focal point of the objective to the intermediate image, given as L, would be very large compared to f0 and fe. Hence, we can then write this equation. This is the linear magnification of the objective lens, whereas this is the angular magnification of the eyepiece that we had discussed in the slide before this. As magnification increases, we will be using smaller objective lens, which means the diameter will be smaller, and the focal length of the objective lens would also decrease correspondingly. In that case, if this diameter is smaller, then the solid angle of the useful ray from the object that is collected by this lens would also be smaller. To produce brighter images, we need to collect more light. In other words, this cone of ray from the object that is intercepted by the objective lens should be as large as possible. If you look at the right side of this diagram here, whereby there's an air gap between the objective lens and the cover glass where the specimen is placed at precision O, the ray that comes from the specimen makes an angle of alpha A, and then it gets refracted and gets collected at the extreme end of the objective lens. If you have rays that are at larger angle than alpha A, after refraction, it will not be collected by the lens. And because of this, it will limit the aperture of the cone of rays that can be collected by the lens. In order to collect light from a larger cone, oil is injected to fill up this air space here. And the refractive index of this oil layer here should match that of the glass cover slip over the specimen, such that the ray that passes through this interface here would not bend much. And then we would maximize the cone of ray that can be collected by the objective lens. In other words, we can then make this angular aperture as large as possible. Hence, the light gathering capability of the objective lens is increased with this oil immersion lens. Next, we would like to define the numerical aperture of the microscope. The numerical aperture is a measure of the light gathering capability of the microscope, and it is given by an expression n multiplied by sine alpha, where n here would be the refractive index of this oil layer or the air layer. This numerical aperture is invariant in the object space due to Snell's law. For the air gap here, the numerical aperture would be given as ng multiplied by sine alpha A, and that's equal to 1 multiplied by sine alpha prime A. The maximum value that you can get in this case would be 1. For the oil immersion lens, then ng sine alpha 0 would be equal to n0 sine alpha 0 prime. The maximum numerical aperture that you can get would be equals to n0. That's assuming that sine alpha 0 prime is 1. And that's where this ray is entering at critical angle. Most microscopes use objectives with numerical aperture that can range from 0.08 to 1.30. And here we have defined that cone of light entering the objective lens correspond to half angular aperture alpha A, which itself is determined by the focal length of the objective. Now, it is known that the image brightness is proportional to the square of the numerical aperture. This numerical aperture is an important design parameter because it will limit the resolving power as well as the depth of focus, in which case the resolving power will be proportional to the numerical aperture, and the depth of focus is inversely proportional to the square of the numerical aperture. For more practical information on microscopy and the various types of high-quality microscopes, you can check out this website here. When dealing with thick lenses, we cannot neglect the thickness of the lens. The image of the first surface becomes the object for the second surface. So the object distance for the second surface must take into account the lens thickness. And there are 6 cardinal points that are used when considering thick lenses, and they are the 2 focal points, the 2 principal points, and the 2 nodal points. And the planes that are normal to the optical axis at the cardinal points are called the cardinal planes. Here we define the cardinal points. Firstly, let's define the 2 focal points. Ray that is at an inclined angle coming from the first focal point. It will enter the thick lens and get refracted and exit parallel to the optical axis. So projecting back the exit ray and the incident ray, they will meet at this point, drawing a normal line from this intersection point that passes through the optical axis, and that's where we locate the first principal point. And likewise for the second focal point, a ray that comes parallel to the optical axis will get refracted through the thick lens and exit at an angle and passes through the second focal point. Projecting back the exit ray and projecting forward the incident parallel ray, then they will meet at this point here. And the normal plane from this intersection point that intersects the optical axis is where we locate the second principal point, H2. So that defines the principal points as well. In a thin lens, where the thickness is taken to be 0, then the 2 principal planes will coincide at the central vertical line that divides the lens. Principal planes can lie outside the optical system. For example, in the meniscus lens, in which this represents the positive meniscus lens and this represents the negative meniscus lens. For symmetric lenses, the principal planes are located symmetrically. For example, in the biconvex lens as well as in the biconcave lens. In planar convex and planar concave lenses, one of the principal planes will be tangential to the curved surface. That's this plane here and this plane here. Defining the nodal points here, an incident ray coming at an angle towards the thick lens will pass through the thick lens and exit in a direction which is parallel to the incident ray, but it gets displaced. Projecting the incident ray forward to intersect the optical axis and projecting backwards the exiting ray to intersect the optical axis, we will then locate the first nodal point N1 here and the second nodal point N2 here. And the plane that passes through the nodal points but perpendicular to the optical axis will be called the nodal planes. In the case of a thin lens, the nodal points as well as the principal points, they all coincide at the mid-plane and center of the thin lens. This diagram here shows the symbols and sign convention used to represent the cardinal points and location for thick lens. There are 2 sets of reference planes or points. They are the principal points, which is H1 and H2 here, and the vertices. That's where the surface of the thick lens intersects the optical axis. So distances that are measured to the left of this reference are given a negative value. Distances measured to the right of these reference planes are given a positive value. Here, distances R and S define the positions of the respective principal points H1 and H2 relative to the vertices V1 and V2, whereas the focal length given by F1 and F2 here are referenced to the principal planes. The basic equations used to calculate the focal lengths the location of the principal planes as well as the position of the nodal points are all summarized in these equations 1, 2, 3, and 4. The image and object distances as well as the lateral magnification, on the other hand, are related by equations 5 and 6, where the object distance and the image distance as well as the first focal length and the second focal length are all measured relative to the corresponding principal planes. In the ordinary case of a lens in air, then n will be equal to n prime, and that's equals 1. You will find that r will be equal to v, s will be equal to w. In other words, principal points P1 and P2 will superpose on the respective nodal points N1 and N2. And F1, the first focal length and the second focal length will be equal, such that we will have the thin lens equation as well as the magnification given by this term. The only difference is that this thin lens equation has a negative sign in front here due to the sign convention that we use in defining this thick lens. This is a qualitative example. We need to find the focal lengths and the principal points for a 4 cm thick, that's here is 4 cm, biconvex lens that has a refractive index of 1.52 and radii of curvature of 25 cm. So R1 here, the center of curvature is on the right side, so it's positive 25. For R2, which is the second surface, the radius of curvature is negative because the center of curvature is on the left side. And this lens caps the end of a long cylindrical tube that is filled with water with a refractive index of 1.33. So firstly, we find the focal length. If we use those equations given, we just substitute all the relevant values inside and you work out that the first focal length is given by negative 35.7 cm to the left, because it's negative here, so it's to the left of the first principal plane, but we don't know where's the principal plane here yet. And the second focal length is positive 47.5 cm to the right of the second principal plane. So next we need to find the location of the principal planes, whereby it is given by R as 0.715 cm, S as negative 2.60 cm, which means that the first principal point is at 0.715 cm to the right of the vertex 1, that is the first surface of the lens, whereas principal point 2 is at 2.6 cm to the left of the second surface of that thick lens. And the nodal points, in this case, because on one side of the lens is air and the other side is water, so n is not equals to n prime. So these values would differ from R and S. So V works out to be 12.51 and W works out to be 14.37. And both these values are on the right side of the respective surface, that is V1 and V2. At the end of this lecture, I hope that you would have learned how to derive and calculate the resolving power of prism, and you would be able to list the various types of prisms and their uses. We discussed about microscopes, so you will be able to define the numerical aperture for microscope. And in thick lens consideration, you will be able to define the useful terms, for example, the 6 cardinal points, and they are measured reference to which planes. And you should be able to apply what you learned to solve problems involving thick lenses. So thank you for watching.